So today we're going to talk about like where those power series come from. So I just gave you a power series before and said this is a function. Its domain are all the x's for which it converges, right? So now the question is how would you take a function that you know about and how would you make it into a power series? And this is really useful because it allows you to approximate functions. Like you can approximate sine and cosine using sort of like an infinite polynomial. Polynomials technically don't have an infinite number of terms, but you can approximate them using polynomials. And I know this is done a lot in physics. For example, like I had friends who took physics classes when they were in undergrads, and they definitely used approximations of things like sine and cosine that were this kind of stuff. Okay, so today's basic idea is that one tool you can use is the geometric series tool. So what is the sum from n equals 0 to infinity a r to the n? What does that equal? When does that equal a number? What number does it equal? A over 1 minus r. And that's true if
R is less than 1.
Oh, and I guess there you go. All right, that's when this thing converges. So what we usually did is we took a series and found what it converged to, right? What we're going to do today is we're going to go backwards. We're going to start with a over 1 minus r, and that's equal to this sum thing, right?
Okay, so we have something we're going to figure out where it converged from.
Yes, we're going to have something to figure out where it converged from, and then we'll figure out what x's for which x's that converges. So see that a is the number that's in the numerator, and it's 1 minus some number in the denominator, right? So for example, here's the easiest one, 1 over 1 minus x. Notice how this is of the form a over 1 minus r. A specifically is equal to
1.
And r specifically is equal to x. You see that? So this will equal a sum from n equals 0 to infinity.
For sure it's 0.
Yep, I am, yes. Yes, I'm positive it's 0. X to the n. If you make it sort of n equals 1, then your exponent is x to the n minus 1. But this is definitely the one I showed you in class.
Yeah.
Okay, so this is equal, and you really don't need 1 times, do you? Like that's not necessary? Let me finish and then you can ask your question, okay? N equals 0 to infinity, x to the n. Now, one thing that's true, this will only converge if the absolute value of r is less than 1, right? Like that's a requirement. And what is r in this case? X. So the absolute value of x is less than 1, which means the interval of convergence is -1 less than x less than 1. Two things, and I promise I didn't forget about you, okay? So first thing is, so do you understand, first of all, that this condition on x, does that restriction make sense? Okay. For geometric series, do they ever converge at their endpoints? Like usually when you find the interval of convergence, you test the endpoints, right? I'm trying to give you an outsy here, so you don't have to write that down every time. Yeah, geometric series are never going to converge at their endpoints. You can think like if you plugged in 1, you're going to have 1 to the n, which is always equal to 1, right? If you plug in -1, you're going to have -1 to the n, which flip-flops, the limit doesn't go to 0, right? So just note that geometric series don't converge at endpoints. So there you go. Okay, yes, your question still?
So it's okay to put n equals 0 just because it's geometric.
That's what our geometric series formula was the sum from n equals 0 to infinity a r to the n equaled a over 1 minus r. So there's no reason why you can't have series start at 0 or 1. It's totally fine. It's just that, and this one wouldn't have any of the undefined problems, right? Yeah, so it's some of them start at 0, some start at 1, some start at 2 or 10 or 1,000, like whatever. But the formula that we use for geometric does begin at 0. Now, sometimes I think WebAssign's a bit picky and it maybe puts the sum in for you and tells you where the series has to start. Does that occasionally happen? I don't remember, maybe not. Okay, so, awesome. Okay, so here's the cool thing that this kind of says. What this says is that if -1 is less than x is less than 1, okay, so if you're in that interval of values, 1 over 1 minus x is equal to, list out the things in this sum. What's x to the 0? 1. And then we have x to the 1, which is x, right? What comes next?
X squared.
And then? You said her, and then? No, and then. Nobody here's seen Seinfeld. Okay, somebody's seen Seinfeld. Look, you have this 1 over 1 minus x is kind of like expressible as in, polynomials aren't infinite, but as an infinite sum of monomial terms. And if you want to convince yourself that this is true, which you could do, if you feel like it, you could go home and graph the function 1 over 1 minus x, like on the interval from -1 to 1. And then you could start like graphing these things and look and see what happens to it as you plug in more and more terms for x's. As you plug in like higher and higher powers, this polynomial is going to get closer and closer to that function. But it's only true within this interval. Okay, kind of crazy, huh? A little bit? So infinite sum equals function you've known and love. And one thing about using this technique is you have to have a minus right here to use this reversal formula, right? It also is the case that this number has to be 1. Does that make sense? That kind of is built into this guy, right? Okay, so like the next one, there's still a 1 here, but what's the problem? There's plus.
Reverse the sign for sure.
Yes, you can make this into 1 over 1 minus negative x to the 5th.
Okay, so
Is that-
you have to algebraically contort it into the right form.
You have to algebraically contort it into the right form. Exactly. That's the perfect way to think about it. You have to mess with it and make it right. And so our a is equal to 1 again. What's our r this time? So this equals sum n equals Gesundheit 0 to infinity a r to the n. Okay. In for a goes 1. Then we have in for r is negative x to the 5th to the n. And I'd like you to simplify these a little bit, as in like do the right thing with those exponents and pull out any like alternating terms. Do you know what I mean by that? I've got negative to a power, right? That's really going to make like a -1 to the n. Does that make sense? Okay, so sum n equals 0 to infinity, -1 to the n. What's the power on x? Is it 5 plus n or 5 times n? 5 times n. So there's the expression for this guy.
Is WebAssign picky about that?
No, but I will be.
Okay.
WebAssign probably will take the first thing, and I'm going to be picky about it because I have seen so many students who can't do exponents right. They just need to make sure that you can, so when you have to simplify, I've like checked it. It's not for just as like algebra 1, but for some reason like people forget. Okay. This one.
Not either.
Oh, crap. Okay, so what's the problem now?
Not a 1.
It's not a 1, okay, it's a 3. So here's what you can do.
By 3?
Divide it all by 3, exactly. Divide the top by 3, divide the bottom by 3. That doesn't change the function, really, right? So now we have 2/3 over 1 minus x over 3.
X thirds.
Exactly. So your a is equal to 2/3, and your r is equal to x thirds. So this is the sum from n equals 0 to infinity, a r to the n. And then plug in your stuff. Your a is 2/3, and the entirety of x over 3 is raised to the n. Oh, don't let me forget to do the interval of convergence. I forgot to do it in the previous one, so. Is everyone okay with the whole plugging stuff in bit of that? Okay, so now the simplifying just a teensy bit. We have 2 and we have x to the n. In the denominator, we have 3 times 3 to the n. What happens to those exponents? Now you add them, so you get 3 to the power of n plus 1. Great.
Wait, why can't we just leave it as the 2/3 times?
Because I'm picky. Okay, let's just leave it at that. It's my
You wanna
fault.
Make it a thing that you can't geometrically work with?
I just would like to see that you can simplify those things, like work with exponents correctly. And so I know this definitely does matter in later stuff, so.
That certain formulas are impossible to use in that form.
Yeah, and it's just also they look messier, so occasionally stuff will cancel too, and it's just nice to actually make it as simple as it can be. Does that make sense? Like, so,
You know,
Okay.
the ratio test stuff and had us breaking that up to get things to cancel.
exactly. So radius of convergence. Actually, to find the radius and interval of convergence, you could technically use the ratio test if you forgot, but you know this was a geometric series, right? So you know the absolute value of r needed to be less than 1, right? So in your case, r is x over 3, yes? That must be less than 1, which implies that x's absolute value is less than 3. And what does it say about x? Between -3 and 3. So you can either list your interval of convergence like that, or you can list it like this. On your take-home quiz, I would suggest like circling it, just trying to not forget to do it, because like obviously it's really easy to do as I just did it.
You wouldn't have to check those?
Hmm?
You wouldn't have to check.
You never have to check these endpoints for geometric series. Yep, so you can just, this is true for all geometric series, and what's even more true about it is the whole strictly less than part. Let's go back to example, well, we'll go back to that one at the end if we need to find the interval of convergence. It's -1 to 1 for the one we didn't do the interval for. Okay, and one last thing and we'll move on. So it's also okay to have like your A include some X's, like that's not a problem. Now, and the other thing that has to happen is when you do this conversion, you have to have this in the form A over 1 minus R, which means this number, the constant, has to be first. So the first thing I'm going to do here is I'm going to flip-flop that 81 and x to the 4th and make this into, nope, I'm just going to put the 81 in front. Like that, there's no changing the sign necessary of that, is there?
No, let's talk about minus negative. So.
Yep, minus a negative, and then we also have to divide by something who's got to make the 81 into a 1, right? Just to divide by 81. So you have x cubed over 81 over 1 minus negative x to the 4th over 81. Do you buy that? Okay.
Did your A be negative? Like, take the
Well, all I did from here to here, is that where you're, is say x,
in the denominator where it's negative, it's minus the negative?
no, because this minus that negative makes back into a plus, right?
So you could just take it.
No, you couldn't just take the negative to the top, because that will make both the 81 and the x to the 4th negative, not just one of them. Does that make sense? Yep, that's the problem. Okay, so sum n equals 0 to infinity. Our A, which is, what?
X cubed
X cubed divided
divided by
by 81, you got that, good. What's your R? Negative x to the over 81. All of that's raised to the n. Okay, so let's simplify this and let's just do it in one go, because I think you guys should be able to get exponent rules quickly. Is everyone clear that there's a -1 to the n thing? Okay, so then with the x's, these exponents are going to multiply, that becomes x to the 4n times the x third
12
plus 3, right? So now that's x to the, and then how about the 81?
That would be 81 Or 1 plus n?
Or n plus 1, but yeah, same thing. Okay. Not so bad, right? Now we need to find the interval of convergence. Well, this will converge if the absolute value of negative x to the fourth over 81 is less than 1, right? Or
Signs are.
if x to the fourth is less than 81. Does that make sense? Okay. So what's going to be the boundary changing point? What number to the fourth power makes 81? 3. So if x is less than 3, and how about will being bigger than negative 3 also be okay?
Yes.
Yeah. So, same idea there. And the reason I can drop the absolute value bars room entirely is that x to the fourth is positive, right? And then this you just kind of have to solve by guessing and checking. Another way to possibly do that, if to make you feel better, is you could have possibly said absolute value of x to the fourth is less than 81. Then you could have fourth rooted. Right, and then you get that x is in between those two numbers. You have a question?
Your radius is actually, your radius would be 6.
The radius is 3, because the radius is half of the length of the interval,
Oh, right.
right? Oh, and I guess the directions have all said centered at 0, but is it obvious that that's kind of what's happening every time? Yeah, we'll do things non-centered at 0 on Monday, actually specifically. We'll talk a little bit about it on Friday, but on Mondays when we'll really do it.
And on Thursday.
Because we're doing more of this on Thursday. Okay. Oh, man, look, this guy. Well, when we integrated stuff like this in the first chapter, I know that was like a long time ago, okay? But remember the technique was to break it up into x over the fraction plus the number over the fraction? We're going to use that same technique. We're going to break f of x into x over x squared plus a squared plus a over x squared plus a squared.
So the way I was gonna do it would have killed a kid.
What were you going to do?
Just the X's and just the A's.
That was definitely a kitten killing mistake, exactly. Yep, don't do that, that's bad. So let's just call this one number 1 and call that one number 2, and we'll find them out both separately, and we'll combine them. So we have x over, I'm gonna say a squared plus x squared, because in this class, your book never, ever, ever states it, but a, b's, and c's are numbers, like constants. X, y, z's, u's, w's, those are variables, they should really say it, but. So how would you first of all make that into a 1? What would you have to do? Divide by a squared, yep, good. So you have x over a squared over 1, and can I just say minus negative x squared over a squared off the bat? Okay, awesome. All right, so that's equal to the sum n equals 0 to infinity x over a squared times negative x squared over a squared. You got negative 1 to the n, x to the, oh, this should be the n power, sorry.
I was wondering.
Yep. So what's x's power? 2n plus 1 over a to the, I think it's actually 2n plus 2. Do you guys agree with that? Okay. Oh, that's not the answer yet. Let's just kind of like, we'll do a half box because it's kind of like half the answer. And because I forgot that it wasn't the answer. Okay, the second one, a over x squared plus a squared. Well, that's a over a squared plus x squared. We still have to divide by,
A squared. Wouldn't that bring an A down?
it would bring an a down. So that's going to become 1 over a instead of, right? A over a squared becomes 1 over a.
Oh, because you don't actually want it to go down.
negative x squared over a squared again. Okay, so that's the sum from n equals 0 to infinity, 1 over a negative x squared over a squared to the n, okay, which is the sum from n equals 0 to infinity, minus 1 to the n, x to the 2n over a to the 2n plus 1. That's half.
Add those sums together.
And you're going to add those sums together. Yep. Exactly. You're going to sum the sums. And technically, I'm pretty sure what you're using here is the fact that these series are actually, because they reduce to geometric series, are actually absolutely convergent, but your book doesn't get that technical about this. So then the original function f of x is equal to first sum plus second sum I hate it when I do that. Click on the wrong thing.
Tony, these can actually add. I thought we were pretty much stuck here.
Yeah, no, these can actually add a to the 2n plus 1. So yeah, so first of all, so what we're going to do is we're going to make it one big sum and we're going to add the terms. We're kind of saying that we can kind of flip-flop the order of stuff we're adding inside of these sums. And that there's technical reasons why that works, but we're not going to go into that in this class.
You can't add those, there's no common denominator.
There's no common denominator.
Oh, wait, I mean, you add them within the sum.
Within the sum, yes, exactly, like this. A to the 2n plus 2 plus negative 1 to the n, x to the 2n, a to the 2n plus 1, like this. And then just factor out any greatest common factors if there are any, and I think there are quite a few, don't you agree? What's the obvious thing they have in common? Negative 1 to the n. There is something else, or actually many something else. X to what power? Huh? Negative 1 to the n, x to the 2n. Okay, great. How about the a's? They actually have a to the 2n plus 1 in common. Okay, so in the first term, that leaves just an x over a. Does that make sense? You can check by redistribution that when you do this, you get x to the 2n plus 1, and then a to the 2n plus 1 again, right? And then I think all that's left from the last one is 1, right? You get a common denominator, whatever, I think that's good enough. We're going to stop. Okay? Is that all right? I mean, you could make that like, okay, we'll do one more. One more step. What could you make that 1 into? A over a. And then you could factor out the 1 over a, couldn't you? I know, okay. So negative 1 to the n, x to the 2n, x plus a over a to the 2n plus 2. Okay, now it's pretty.
Is that the thing that'll get you full credit?
Yeah.
The one above it will get you partial credits?
I think probably we can count on Caleb and Jody being a little picky about this. So yes, just get a common denominator. It's not going to kill you. I was just being lazy, and I shouldn't be lazy because I want you to be lazy. Yes?
Are we ever going to be doing interval of convergence on these problems, or?
Well, we're doing that just because they're geometric.
Okay.
So let's do that for this one, then we'll do the last example. That's like a warm-up for next time because it will function quite well.
Okay.
So the interval of convergence here is, both of them have the same r, right? That's the weirdest noise. We need negative x squared over a squared to be less than 1. Okay, just, yeah, ignore it. Which means x squared absolute valued is less than a squared. That noise is freaking me out. If x squared's Let's think about it this way. Absolute value of x squared is less than a squared. We'll just squeeze. You write big. Put it below. So what's x between? Negative a less than x less than a. But I think what you were asking for interval of convergence is, do you have to check the endpoints? And the answer is no, because they're all geometric.
Is this square root for everything?
No. Because it's time and we don't have time to spare. So this first one is going to review the ideas from all the previous examples. It's just that you're going to find two power series and add them together. So the first thing you're going to do, which is kind of good review of integration, it's a good review because this applies to integration techniques too, is to first find a partial fraction decomposition of that polynomial of this thing. So we have 2x plus 3. How does that denominator factor? Great, x plus 2, x plus 1. And the thing is, you know how to find power series for things like something over x plus 2 and something over x plus 1, right? So if you break this into a over x plus 2, b over x plus 1, once you figure out what the a and b are, you can find power series for the first thing and the second thing. Does that basic idea make sense? Okay. All right, so you multiply by the denominator, which gives us 2x plus 3 equals a times plus b times x plus 2. Okay. And this is one of those nice ones where you can just input clever values. If we input x equals -1, what do we get on the left side? Good. Equals, I think just b. Is that right? Okay. I never trust myself. For good reason, as you guys know. What's the next number I plug in? 2. And when you plug that in on the left side, you have -4 plus 3 makes -1. Great. Equals, I think this is just a times -1. So that's nice. A is also 1. Okay, so f of x is equal to 1 over, I'm going to write that as 2 plus x plus b, 1 over 1 plus x. Is that okay?
Partial sums is something you never really get the opportunity to forget.
No, you won't get the chance to forget partial fractions. Okay, so now to use the whole power series reversal thing, you have to do two things. You have to have this first number being a 1, right? Which it is in this case, so that one's good, right? You also have to have this as a minus sign, right? Okay, so for the first one, how would I make that into a, the 2 into a 1? Divide by 2, yep, so divide by 2. Divide by 2, I love that I can color code on my iPad. Makes me so happy. Okay, that becomes a half over, and can I say 1 minus -x over 2 right away? Okay. Over 1 plus 1 minus -x. And just a reminder, we were using the geometric series formula, which says the sum from n equals 0 to infinity, AR to the n is equal to what?
A over 1 minus.
Great, exactly. And this is if or for absolute value of r less than 1, right? Okay, is that all right? Okay, so for the first one, just this guy, what's that become? So it's the sum, n equals 0 to infinity. What's the a?
Over 2.
And what's the r? To the n, right? And the second one, what's the a? And the r is just -x, right? Okay, now a couple things to note here. This is true if the absolute value of negative x over 2 is less than 1, right? That's the first R. Does that make sense? Yes?
This is the on the second one.
Yes, it should be the and the second set. Thank you. Now, does that require, the R requirement make sense? Okay, that implies the absolute value of x is less than 2, right? What is that as an interval? What's x? Negative 2 to 2. So that's what's needed for the first series to converge. Is the second series different? It is. And you also need that negative x is less than 1, which means that, what's x between? Negative 1 and 1. So you need both of these to be true, as in where does this happen and that happen? Do you see why? Because the first one has to converge and the second one has to converge. So and means where do those intervals overlap, which in the fancy mathematical word for that is intersection.
Isn't it just negative 1 to x to 1?
It's negative 1 to 1. Does that make sense? So this, they overlap or intersect from negative 1 to 1. So that's going to be the set of x's for which the series will converge. And once you know you're in there, you can simplify this sum a little bit and write it as one sum. Oh, so what do both sums have in common that's kind of like a greatest common factor? Negative x to the n. So which really is a negative 1 to the n, x to the n, and the other stuff is 1 over 2 to the power of n plus 1, and then just plus 1. Does the whole 2n plus 1 make sense? Does that make sense why that is what it is? Because you really have this 2 to the n, right? Times 1 more 2 and the exponents add, right? Okay. So the kicker is there is you have to look at both of the intervals of convergence and look for where they overlap. Otherwise, you couldn't do what I just did, basically. Yes?
Why was it needed to find the overlapping?
Oh, because in order to say that this whole thing converges, this has to converge and that has to converge. And there are some x's for which this guy will converge, but the second one won't. So the first one will converge if x is between negative 2 and 2. That makes sense? This second one will converge if x is between negative 1 and 1. Right? That makes sense? For them both to converge at the same time, you have to be in the stricter interval. Like if you had, say, negative 1.5, you plug it into the second one, that second one's going to diverge, even though the first one converges. So some number plus infinity is still infinity.
So would you have to find the overlapping if you didn't combine?
You have to find the overlapping pretty much no matter what. And then finding the overlapping tells you that this combination is true as long as you're in that interval. But yeah, even the uncombined part will only converge if both parts converge. Okay. All right, so does everybody agree that this trick is like slightly limited in some sense? You know what I mean? As in, we only can find power series for things that are geometric, right? Which is kind of a limited class. And the way we're going to extend that just a little bit today is we're going to use derivatives and integrals to find series as well that are related to these guys somehow. And then tomorrow, there will be a lesson where you do something called the Maclaurin series, which does this for any function, and there's a specific pattern that those terms follow. Okay. So the sum of a power series makes a function whose domain is the set of all x's where your series converges. Sorry, I made that kind of small. So what we want to do is we'd like to be able to differentiate and integrate these functions kind of like we do polynomials. Like, so if I gave you a function, f of x is x to the fifth plus 3x to the fourth plus x cubed plus 2x plus 1, you can take the derivative piece by piece, right? Does that make sense? What I'd like to kind of do is do the same thing with an infinite sum, except for it's an infinite number of things instead of a finite number of things. And we're not going to prove the theorem, but we're going to use it. So if we have this power series, and it has the radius of convergence r bigger than 0, then this is our function. That's our power series function. And it's differentiable on the interval a minus r, a plus r. That's just like saying on the interval of convergence, you can take its derivative. And now think about this. If you take the derivative of that f thing, c naught is a number, right? What's its derivative? 0, right? Okay. What's the derivative of c1 times x minus a gonna be? Just c1. Does that make sense? What's the derivative of c2 times x minus a squared gonna be? 2c2.
X minus A.
Uh-huh. And let's just pretend I had one more there. The next term would have been c3 x minus a to the third, right? So the derivative of that guy would be 3c3 x minus a squared, etc., right? Because it's sort of a generalized infinite polynomial, sort of, right? Okay, now if I'm going to write that as a sum, you could start the sum at 0, but why is it easier not to? What happened to your 0 thing? It's gone. So I'm just going to start this sum at n equals 1. Okay. All right, and then what's the pattern there? You have the Cn, right? So C1 for the first term, C2 for the second, C3 for the third, right? So you have the Cn. How do you, and then there's really like one C1 there, right? 2C2 there. What does that become when you put it in the summation notation? It becomes an n, right? Like a regular old n. And what's the new power on x minus a? N minus 1. So look at how on the C3 term, the power is 2. One less, right? And look at what happened. So in this sum formula, the derivative of Cn's a constant, right? So it doesn't change, we take the derivative. What's the derivative of something to the n power? You pull the power down, right? And then what does the new power become? N minus 1. So you can, and the only thing you gotta remember is that, oh yeah, my first term, my C0 is gonna go away. So I just start my sum at n equals 1 instead. And that should make sense. We just think about it as a list and say I take a derivative piece by piece. Is that okay? Yeah.
What does it mean by like the a minus r?
That's your interval of convergence. So when you found the interval of convergence, you had some center point A, and your power series converged r units above it and r units below. So to go above a by r units, that's a plus r, and to go below a, it'd be a minus r.
So they're not centered at 0.
Not necessarily centered at 0, but if it was centered at 0, then your interval would be like, minus 2 to 2 or something like that. But some intervals we found, like in the section 11.8, were like, negative 5 to 7 or something weird like that, right? This just lets your intervals be not centered at the origin, or 0. Okay, so there's the idea for differentiation. So the kicker is you lob off the first term, and then you just differentiate the part that's got x's in it. Integration isn't all that much harder. What's the integral of c naught? C naught x, right? And this is the one tricky thing. I'm going to say c naught times x minus a. And that's going to allow us to use a general pattern, and it's because you kind of have this whole general constant, you could add on the end that it's okay to do that. Does that make sense? Because c times a is just a constant, and you can kind of have your plus c at the end compensate for that. Well, and what's the antiderivative of c1 times x minus a? C1, what's the new power on x minus a if you anti-differentiate?
That's squared over 2.
Squared over 2, exactly. How about C2, x minus a is going to be all to the third over 3, etc. So this time we didn't lob off that first term, so let's still begin our sum at n equals 0. The c sub n's don't change, but now what's the power on x minus a? I think it's n plus 1. Because you think about this,
Start at 0.
you see that? Start at 0, exactly. You see you have C1, and the power is 2 over 2, right? So, and also I need to have this over n plus 1. And you do have to lob on like a big old constant plus c on the end.
Is that like an integral?
It's an integral, yeah. You integrate this piece by piece. And just look at this thing. If you integrate something to the n power, the antiderivative of something to the n is that something to the n plus 1 over n plus 1, right? And these c's don't matter. What freaks students out is they see those c's and they think like, there's letters and variables in them. But they're really constants that are in front of each term of this like polynomial thing. Ish. Okay, and then the theorem, the useful thing is that the radii of convergence obtained by differentiation and integration are the same as the original. So if you know your original series radius of convergence, that's the radius of convergence of your differentiated or integrated power series. They're the same, always. What might change is the endpoints. So same R, but whether or not you include those n's will be different. You'll have to retest them. Okay, but you have to go through the ratio test to find the R again, for example. That part's unnecessary. Okay, let's just do a really easy derivative. This function looks like crazy crap, okay? But once you figure out, and we can do the integral too because it's not very hard. Once you figure out which part's the constant, it's not very difficult. So let's write this as the sum from n equals 0 to infinity, negative 1 to the n, over 2 to the 2n, n factorial squared, times x to the 2n. Is that okay?
So you didn't change anything?
I didn't change anything, I just kind of pulled the n's out because they're the constants. They're like the c sub n things, which didn't change in our derivatives in the past, right? So then f prime of x is the derivative of this guy. And which part and technically you can kind of think about just derivativing, it's not a technical word, but I just recorded myself saying, derivativing the x thing. Like only that part matters. The rest of it's just constants.
No.
So the first thing is when we derivative, we have to start our sum now at n equals 1 because of the whole first term going away. This stuff, is it going to change? That stuff is a constant, so it will not change. It's negative 1 to the n, 2 to the 2n, n factorial squared. This is the thing that you differentiate, because it's the thing that's x to a power, or it's the thing that's a function of x. So what's the derivative of something to the 2n power? 2n, x to the... There you go. And we're not going to simplify it any more than that. That's the derivative. Awesome. Okay?
So why did you re-index again?
We re-index because if you look back at the previous list, notice how the derivative of c naught was 0, which meant that 0th term is gone. So since it's gone, you just start your sum after it. If you did like the second derivative, then the first and second terms would be gone, the 0th and the first. So you begin at n equals 2. And sometimes WebAssign might make you then take this, if you want to begin this at 0, you got to take this thing and then re-index it. Okay, so you have to start with this guy and then kind of change this to 0 and then change the exponents, the ends appropriately. That's just tricky. It's easier to think that first term just goes away. Let's do the integral too, because I didn't ask you to, but it's not that bad.
Starting that, and I crossed it out the moment I saw it wasn't on the instructions.
Okay, so you have the integral of the sum. Oh, that should be 0, sorry. Negative 1 to the n. 2 to the 2n, n factorial squared. And this is the original function, so it's x to the 2n. So with the integral, do we have to start our sum someplace different? Nope. Okay, so sum n equals 0 to infinity. Which part of this are constants and don't matter?
The first piece.
Negative 1 to the n, 2 to the 2n, n factorial squared, and then you integrate x to the 2n plus 1, which is, or x, I just told you what it is. What's the antiderivative of x to the 2n? X to the 2n plus 1 over, and then because you did an antiderivative and you have to plus c. Sometimes you can figure out what the c is and sometimes you can't. It just depends on the situation. In this case, we have no information, so no idea. But you get the idea that the stuff that has n's are constants and then the x's are what things you're... Okay. So here's how we're going to use it. So just take a look at example 6 and think about it for a sec. It looks a lot like our geometric thing, doesn't it? But not quite, because it's squared, right? And you can't do partial fraction decomposition because when it's like the same factor raised to a power, that already is its partial fraction decomposition, so...
You can just square root both sides then.
no, because then you have, no, you cannot. Because then you'd have to like try to distribute your square root over like an infinite sum, which would kill a lot of kittens. So here's the thing. So this gives you a hint and says you're going to use differentiation. And you kind of use integration and differentiation. It's confusing, but this isn't how I keep it straight. So I know if you integrate, you write that as 1 minus x to the negative second. What do you get? First of all, it is f of x, right? I just rewrote it as negative power. So the antiderivative of something to the negative 2 is that's
to the negative 1.
To the negative 1 over negative 1. And then why would I multiply by another negative 1? Because of the inside thing, right? Kind of like the reverse chain rule. So this makes 1 over 1 minus x, right? Do you buy that?
Does that look like that?
And is that thing something we can work with using geometric series? Yes.
Would it not be negative?
You multiply by negative 1 again.
You multiply by negative 1 again because of the fact that it's 1 minus x inside of the power. Like think about, right, I mean, if you take the derivative of this guy, 1 minus x to the negative first, suppose that's your function, just call it y, right? Y prime is negative 1 minus x to the negative second times a negative 1 from the chain rule, right?
Okay.
So this first negative 1 here comes from the power rule, right? This second negative 1, where's that coming from? Derivative of the inside thing. That's why it stays positive. Okay, so because this is true, and we could actually even add plus c. So then the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared, right? Do you buy that? So here's the thing. The question said to use a derivative, but you've got to figure out the thing that you're going to differentiate in the first place. And the way you figure out what to differentiate is you figure out what the antiderivative is, and then say, okay, because of how this relationship works, therefore this derivative is equal to the stuff inside. So you have to use both directions. If I differentiate, I have to write it down, anti-diff 1 over 1 minus x squared, what do you get? 1 over 1 minus x, right? If I differentiate, which one do I differentiate to get the other, that is? If I differentiate 1 over 1 minus x, I get 1 over 1 minus x squared, right? Okay. So here's the thing. You either can integrate something you can find a series for, or you can differentiate something you can find a series for. Which one should you do? Which one can you find a series for? Can you find a series for this guy?
Yes.
Yes. And then could you take its derivative? Yes, which would then give you this guy. But you had to integrate to figure out what to stick inside the derivative in the first place. So you're always going to use them both, and it is definitely tricky. I'm sorry, I can't fix it. So this tells you 1 over 1 minus x squared equals the derivative of 1 over 1 minus x. Which equals the derivative of the power series and equals 0 to infinity. What's the power series for 1 over 1 minus x? It's a really easy one. Is it negative x to the n or just x to the n?
X to the
I think it's just x to the n. Right, because the negative is part of the geometric series formula, right? Right, that formula is a over 1 minus r, isn't it? Can you differentiate that thing now? So what changes about your sum? Where does it start now? N equals 1 to infinity. And differentiate x to the n. What's the derivative of x to the n?
Tan x and n minus 1.
And x to the n minus 1. Okay. But you just gotta buy that. I know that it's convoluted how you figure out what to differentiate. But do you buy this relationship? Yeah, and then you just use your power series thing, right? You take your derivative. We know that this guy at that stage converges if the absolute value of x is less than 1, right? Which means that your r is equal to 1, right? This guy is also going to have r equal to 1. So you have this negative 1 to 1 interval because you're centered at 0. You should technically test those endpoints. They're both going to diverge. If you plug in x equals negative 1, you get this guy. Negative 1 to the n minus 1 times n. You plug in x equals 1, you get the sum n equals 1 to infinity. I think just n. Is it clear that those both are going to diverge? So test for divergence on both of these. Yes?
Is that lowercase r the same as uppercase?
Yeah, but I should be consistent.
Just making sure.
Yep. I don't remember what WebAssign makes you do, but I think, so just because it wouldn't hurt to practice, WebAssign might make you re-index these guys. Do you want to practice that?
Yeah.
Yeah, okay.
We index it to 0.
Yeah, we're going to re-index to start at 0. And I'm just going to think about this. So think about when I plug in 1, I get, this is like a first term, I get 1 and then x to the 0, right? So if I plug in 0, I should also get 1 in my first term here. So what does that n have to become?
N plus 1.
Has to become n plus 1. Does that make sense? And then what becomes of the x to the power? I think it's just x to the n now. And you could verify that those are the same thing, but just like plugging in numbers beginning at 1 for this guy, like let's see what comes out. Plug in numbers beginning at 0, let's see what comes out, and they're gonna match. Like that first one, you get 1 x to the 0, 2 x to the 1, right? This one, you get 1 x to the 0, 2 x to the 1, etc. So
WebAssign will have a box with the,
I have seen WebAssign having a box that like gives you the summation part of it and indexes it. I think I remember that. Does that make sense? Like in the box, they have the sum sign and then you put in what the stuff is. And so they've forced a certain beginning point on you. Sometimes they do that.
is it ever going to be anything other than 0 or 1?
It will usually be that they re-index it back to 0. But if they don't put that, then I think it should take either one. As in, like, and in that case, don't re-index because it's more work, you might make a mistake. Okay. ln of 1 minus x. The hardest thing with these is figuring out what pattern to use. Like, it's tricky. Okay. So, I don't know. It's not super easy to, and actually, I'm going to change this because your book does ln of 1 plus x. So let's just do ln of 1 plus x.
Can't you just take the derivative and then you get 1 over 1 plus x?
Yeah, so the derivative of natural log of 1 plus x is equal to 1 over 1 plus x, right? So then do you buy that the integral of 1 over 1 plus x dx will equal natural log of 1 plus x? Do you buy that? Take the derivative of your function to figure out what you're going to have to integrate to get that back. Yeah, technically, but our power series only care about positive x's, so we're not going to worry about it. Okay, so then what we have is that ln of 1 plus x is equal to the integral of 1 over 1 plus x dx. Can you write that 1 over 1 plus x as a geometric series?
1 over 1 minus negative x?
Yeah, so your a is 1 and your r is, you have it right, just tell me,
Negative x?
negative x. So negative x to the n dx. You buy that? Now here's why I've been harping on simplifying and pulling out constants. Because I'd like you to be able to integrate without having to use the chain rule. Does that make sense? Because it's easier, right? So this, if you don't take out the negative, it makes the integration really, like, a little bit trickier, and almost everybody that I've seen try that does it wrong. So simplify your thing, pull out your negative. You see what I mean by that? Like make this into the integral sum n equals 0 to infinity, negative 1 to the n, x to the n. Do you buy that? Okay. And now what's the constant part and what's the part you integrate? The negative 1 to the n is the constant part and the thing you integrate is the x to the n. So that's the sum. N equals 0 to infinity. Negative 1 to the n. What's the antiderivative of x to the n? Almost. X to the n plus 1 over n plus 1 plus some constant c. Okay, your book, just to be a royal pain in the behind, re-indexes it to this. Well, because it's just nice that it's x to the n over n. Does that make sense? Do you buy that they're the same thing? So the sign of the first term in this thing is, when we plug in 0, we get positive 1, x to the first over 1, right? In this one, when I plug in 1, I get negative 1 to the 0, right? And then I get x to the 1 over 1. So they just re-index instead of, going from 1 back to 0, they went from 0 up to 1. So I don't care which one you give, but just know that the one in your book is this one, and they're equivalent. Ready for one more crazy one? Okay, how about
Are we
arctan?
doing the radius of convergence?
Oh, the radius of convergence is just 1, because the radius of convergence of the original series was also 1. The endpoints, I think you'll have convergence at both of them because of the AST, but I'm not positive. It's not very hard to check. Okay, how about this guy, arctan? It's a lot like ln. What happens if you differentiate arctan?
You get 1 over 1 plus x squared.
Yeah, which is something you could actually kind of work with, right?
That squared there doesn't change anything?
Because we can just plug in r is negative x squared.
Okay.
Right? We did that in previous examples, didn't we? Okay, so this is true. So the integral of 1 over 1 plus x squared is going to equal arctan. Okay, so arctan of x. 1 over 1 minus negative x squared. So write that ratio as a sum. It's the sum from n equals 2 infinity, right? And your a is 1 and your r is all to the n power, right? Okay. And just so I don't forget it, can you find the radius of convergence? Negative x squared, absolute value must be less than 1, right? Which really means that the absolute value of x squared has to be less than 1, right? Or what's x between? Negative 1 and 1. And that's going to hold, the endpoints may change, but that relationship will hold throughout the rest of the problem. Class next is super noisy. Okay, negative 1 to the n. What's the power on x now? 2n. Great. And then integrate the x part. What's the antiderivative of x to the 2n? Say that one more time.
X is 1 plus 1.
X to the 2n plus 1. Very good. Over
1 plus 1.
2n plus 1. Now technically you need a plus c here, but we have this thing is equal to arctan. Okay. Can you use that information to figure out what the c is? What if I input, what's a nice value to input for x?
1.
What's your very, very favorite number?
0.
0. Inputting 0 is super nice because when you input 0 into this like power series, everything goes away, right? Does it? Maybe your first term. And 0.
0 is in.
Yeah, because you have 0 and then.
And 0, when you plug in n equals 0, it'd be 0 to the first power, so it's all gone. So what you have then is arctan of 0 is equal to your c, which implies that c is actually just equal to 0, which will happen in some cases, but not all, okay? Okay. Let's just check the n's real quick. Okay. At x equals -1, we have the sum from n equals 0 to infinity, -1 to the n, -1 to the 2n plus 1, over 2n plus 1. And the question is, does that still alternate? Let's see. First of all, do you buy that this is the same thing? negative 1 to the 3n plus 1. Does that make sense?
Yeah.
Okay, let's just plug in some numbers. When I plug in 0, this is negative, right? When I plug in 1, this is now 4, and so it's positive. When I plug in 2, this is now power of 7, so it's negative. So it is flip-flopping, right? So this is going to converge by the AST. That's the harder of the two. Okay, the next one's even easier. Because when you plug in x equals 1, what do you get?
Negative 1 at the end.
Over 2n plus 1. And that's totally obviously alternating, right? There's no, no questioning, does this 3n plus 1? I showed this. It's negative 1 at the end. That flip-flops, obviously, right? This guy's always also going to converge by the AST. Yes?
Doesn't matter whether or not your first term in the series is a negative or
Nope.
not?
Nope. It can flip-flop either negative positive or positive negative as long as it flip-flops.
And it will still converge?
Yes. Yep. It doesn't matter that it's kind of like the eventually decreasing. There's no specific order on the flip-flopping. Yeah.
So the general strategy here is that we're integrating and deriving and doing whatever manipulation we need to make it into the electric.
Exactly. Yep. The general strategy is you integrate or differentiate whatever you, and you kind of always end up using both of them. Does that make sense? So I'm pretty sure the WebAssign questions that you're given on stuff like this tell you what to do, as in they prompt you, on the first one where I said you're going to eventually use a derivative, but you've got to use an integral to figure out what you're going to derivative. So there'll be some prompting. You just have to try them because they are tricky. You just got to do a few to kind of wrap your brain around it. Just like I can't watch basketball and learn to play it. Now, another thing you can use is these are now formulas. Okay, ready? You still here? Kate's looking kind of zoned out on me. So these are formulas, and now you can use them. So this example, do you see how I have f of x equals ln of 1 plus x squared? What we had a formula for if I had f of x equaled ln of 1 plus x. This was the sum from n equaled 1 to infinity, negative 1 to the n minus 1, x to the n over n, right? That was the re-indexed version. Does that make sense? Do you see how here I just have x squared instead of x? So what you can do for f of x is just input x squared for x in that formula. So this would be a sum from n equals 1 to infinity, negative 1 to the n minus 1, x squared to the n over n. And then what does that simplify to? Negative 1 to the n minus 1, x to the 2n over n. Yeah.
Would you not need a 2n in the denominator?
No, you don't.
That would be produced if it was 2 plus x squared, right?
I don't know about that. But the thing is that think about, instead of this being x, that could be a u. And so you can replace the x by something else. So if you do it the long way, there's another way to do it. So you could have also said, well, f prime of x is x over 1 plus x squared, right? Yes? So then you could have said the ln of 1 plus x squared is the integral of x over 1 plus x squared. That would work too. Then you can find a power series for this. So that would be integral x. So in finding that power series, what is your a? X. What's your r?
Shouldn't f prime of x be 2x?
Yes, it should be 2x. There we go. Okay, thanks. So your a is 2x. So this is negative x squared to the n. So do you buy, other than this me missing my 2, do you buy that part of the computation? In particular, Mitchell, because I'm doing it kind of for you. Do you understand this part of it? Okay. So now, when I simplify this, before I integrate, I have the sum from n equals 0 to infinity. I have a 2. I have a negative 1 to the n, right? And then what's the power on the x going to be? Obviously, there's a 2n. What else is there? Plus 1. Do you see where that comes from? Okay. Now, anti-differentiate x to the 2n plus 1. N equals 0 to infinity, 2, negative 1 to the n. You get x to the 2n plus 2 over 2n plus 2. And then what happens to the 2's? And you can crank a little bit because this doesn't match what I wrote down over there. X to the 2 parenthesis n plus 1 over. So do you understand the thing that happened on the right? Yes? Okay. Why is it the same as the thing I gave on the left? What did I do? What would you do to this answer to get that answer? You just reindex it. So to answer your question, the answer is no. These things are formulas that work for any value of x, and what might change is your rates of convergence. Yeah. Yes, this 2 on the bottom should be gone. Yep. So if I gave you, for example, if I'd given you f of x equaled ln of 1 plus 3x, what would you plug into this ln formula for x? You plug in 3x. If I'd given you ln 1 plus root x, you can just now plug in root x. Always going to work. So once you have something, a formula for like ln of, say, 1 plus a general thing, you can input any argument. And there's no weird, like, multiplying by a derivative stuff. It's just input that argument. And I should kind of convince you that it works. It's weird.
Well, I think the only place where I messed up was just that I got the derivative wrong.
I see.
Instead of x over 1 plus x squared, I got 1 over 1 plus x squared, and that's where...
And that'll mess it up.
It's different.
Yep, exactly. What does your note say? What do you guys have? Do you have this one?
Just, yes.
X, okay.
Yes.
So we have a formula for arc tan of x. That was equal to a sum n equals 0, was it 0 to infinity? Negative 1 to the n, x to the 2n plus 1 over 2n plus 1.
And we figured out that c equals 0.
We also figured out this one that we had a radius of convergence equal to 1, right? And we figured out c was 0, exactly. So our function g of x is x cubed times, can you use that power series that you know to get the power series for arctan of x squared? What could you plug in for x? X squared. So you see how this says arctan x, this x is that x. Like if you want to find arctan of 5, you could plug in 5 for x, right? Actually, you can't plug in 5 for x because 5 is outside this range. If you want to find arctan of 0.25, you could plug in 0.25 for x. Okay, so this becomes the sum, n equals 0 to infinity, negative 1 to the n, x squared to the 2n plus 1 over 2n plus 1.
And it still needs a lot of simplifying.
It still needs a lot of simplifying, but it's not so bad now. It's easier than trying to like figure out, should I differentiate or should I integrate, right? And this idea is going to come up a lot in tomorrow's lesson too, so it's good to be familiar with it. So first of all, inside that sum, what is the exponent on the x?
4n plus 2.
4n plus 2, do you guys agree? By that? Those exponents multiply, right?
Yes.
Okay. And then when you bring in the x cubed, what happens to the exponents? They add or multiply?
Multiply. No, they have.
They add. So it's negative 1 to the n, x to the 4n plus 5.
You just plug it in right into the sum.
Yeah, it's kind of like saying you can do this like infinite distribution. Like think about this thing, the sum as you'd expand it out, and then everybody would get an x cubed distributed to it, which means the powers are all gonna go up by 3. Does that make sense? Okay. So for those, make sure you know that you can use previous stuff.
But if the powers are all gonna go up by 3, then why didn't negative 1 to
The
the,
powers on the x's all go up by 3.
oh,
Does that make sense?
yeah,
The positivity and negativity isn't affected by multiplying by x cubed.
alright.
We still have to prove that our C is 0.
No, if your C is 0, it's 0 still. Okay. All right, this guy, I can show you 2 ways to do this one. And one of the ways, so do you want to do the derivative way first?
Yes.
Yeah, okay, so f prime of x is equal to what? Almost. Negative 1 over 4 minus x. I think I'm going to avoid trying the other way because otherwise it kind of sucks. Okay, I'll show it this way, it's easier. So then the integral of negative 1 over 4 minus x dx is going to equal ln of 4 minus x, right? Plus some constant c. By that?
Yeah, so doing the long way is actually easier in this instance.
Yeah, you can somehow make the other formula we have for ln work, but it's tricky and I don't want to go there. At least not today, maybe a time when I have some spare time. Okay, so ln of 4 minus x equals integral That's the relationship that we need, right? Do you buy that? Do you believe that's true? Okay. Because if the derivative is this, okay, so can you...
Divide
can you-
everything by 4?
Divide everything by 4, yep. Then you can use the geometric stuff to make a power series. So that becomes integral of the sum. So negative 1/4 is my A. What's your R? And your mean picky teacher says pull out those constants. It makes your life easier. Integral of the sum. Negative 1 isn't raised to the n, right? Because it's just that first negative 1. What's the power on the 4?
16.
I think it's not 16. I think it's n plus 1. And then just times an x to the n, right? Okay. So now which part is getting integrated?
Yeah.
X to the n? X to the n plus 1 over n plus 1, and then plus some constant c. And really, I don't care if you reindex these things, like, it doesn't matter to me. So don't bother. Okay, so this thing is equal to ln of 4 minus x. Does it make sense? It's going to be a good idea to plug in x equals 0 to find that c? Yeah?
Oh,
Okay,
the
so-
natural order 4 still exists.
Yes, exactly. So at x equals 0, on the left side we get ln of 4. On the right side we have just c. And there's no need to rewrite it. If you figure out what c is, like, we're done.
Wait, can't you raise both of those to the E? The AC?
But then you're gonna have like this sum, no, don't go there. You have the sum inside of an E, and yeah, you can't just like apply E like wherever you want. You can't just like, I'm gonna E here, and E there, and E there. That's
No,
that's
both
silly.
both sides of the
Yeah, but then you're gonna put that whole sum into an exponent. I don't see why that's better. It's never done.
It's gonna make
Okay.
it worse.
It's gonna make it worse. We're just not, it's a reasonable idea, but we're not gonna do it. Okay, sorry. All right. If at the end I have time to show you the other way, I'll show you the other way because you can actually use the other LN series that we had to do this too, okay? But
The interval convergence then is,
yes, thank you. This converges if, what was your R? X over 4 is less than 1, right? Which means that the absolute value of X is less than 4. So your radius of convergence is 4.
and your interval is -4.
Your interval, your starting interval is -4 to 4 not including. I think that one of those numbers gets included. I'm not sure if one gets included. I'd have to work it out to be sure. I think actually they're both not included, but I think what you're asked on your homework more often is what is the radius of convergence. So I suspect, I know that this will diverge at x equals 4, because when you plug in x equals 4, this cancels and this cancels, right? You have -1 over n plus 1, basically a harmonic series that's negative, that diverges. When you plug in -4, you get -4 to the n plus 1. I think this -1 makes it always positive. It's also harmonic. I think it diverges at both 4 and -4. But let's talk about what we're going to use these things for, because you can use them to approximate series, which is kind of cool. Or approximate antiderivatives. So with all the techniques that you learned, did you ever learn how to antidifferentiate 1 over 1 plus x to the 7th? Nothing we know can help us do that, right? Not off the top of your head anyway, right?
Why'd you ask us?
Well, what we're going to do is we're going to use a power series.
Why not use U sub?
Why not use a u sub? What would need to be there what would you u sub?
X.
X to the 7th? Or the whole thing? There's no x to the 6th there, so you can't do a u sub, right? I mean, you need the whole du to be present in your integral, so I don't know. So this is a common thing for a function. I don't know how to integrate that function, guys. Like, I ain't got it. So what you can do is use a power series and use this whole integration stuff we just learned. So write this as a power series. So it's the sum from n equals 0 to infinity. What's the A? What's the R? Negative, and it is negative, isn't it? To the n. Okay, so this is the same thing as the sum from n equals 0 to infinity, -1 to the n, x to the 7n. So the integral of 1 over 1 plus x to the 7th is equal to the integral of this gigantic something. That is a 7n up there in the corner. Yep. Oh, and by the way, at that stage where we made it geometric, this is true if the absolute value of -x to the 7th is less than 1, which implies that x is less than 1, right? Divide 7th root 1, you still get 1, right? Okay. Now, can you integrate x to the 7n? No, come on. No, you can. X to the 7n plus 1? Exactly. And technically there is a plus c, which you can't figure out because you don't know what the original function is. But hey, you have an antiderivative. It might be an infinite sum, but it, still function for specific values.
Can you try converting this back into an actual function?
Maybe. I don't know. It's not part of my plan for today anyway. So now we're going to use that in part B to find the integral from 0 to 0.5 of f of x to within 10 to the negative 7th. It's really small. So if you were doing a definite integral, you find your antiderivative, right? And then you plug in your first number minus plug in your second number, right? With definite integrals, does the plus c matter?
Nope.
That goes away, right? So what I have is this big old sum thing, which is my antiderivative. So x to the 7n plus 1. Or 7n plus 1 evaluated from 0 to 0.5.
Are we sure we're gonna be that?
Is that okay?
We're gonna be that accurate though?
Or, yeah, it's not gonna be that hard. It only takes, I think it takes 3 terms. It's kind of crazy. Okay, so now, first of all, the x's that you can plug into this function for convergence are things between negative 1 and 1. So is 0.5 between negative 1 and 1? Yes, good, okay. So now you plug in those numbers, the 0.5 and 0 for x. So what happens when you plug in 0? Everything's gone. Does that make sense? Plugging in 0 for x means that last sum is 0. So sweet. All you have here is the sum from n equals 0 to infinity, negative 1 to the n, 0.5 to the 7n plus 1 over 7n plus 1. So that infinite sum gives you the value of this definite integral. And we want to estimate it, and we're going to use the AST remainder theorem. Why do I use that one and not the integral test remainder theorem? It's also it's because it's alternating, and thankfully it's also the easier one, right? So there we have that the error was less than or equal to, it was bn plus 1, right? Which we want less than 10 to the negative 7th, which is 0. What? 1, 2. Oh God, I lost track. How many zeros is that? 6? Okay. Okay, you gotta be teensy bit careful how you input n plus 1. By which I probably mean you're gonna need, when you're being careful, you're putting stuff inside of parentheses. So bn plus 1, the bn start as the positive part of the alternating series thing, right? So you have 0.5 to the 7 parenthesis n plus 1 plus 1 over 7 parenthesis n plus 1 plus 1 less than 0.0000001. Decimals really should have commas too, shouldn't they? Yeah.
I'm not sure why you're putting everything in all of n plus 1 in, oh wait, never mind.
Got it?
Yep.
7n plus 8. Were you confused about why I need the parentheses?
Yeah, but, yeah, I figured it out.
Okay. But the basic idea for the rest of you, in case you had that question too, is that to find the n plus first term, you must just replace the n by n plus 1. That's how you do that.
It's just 6 zeros and a 1 for that decimal, right?
Yeah, exactly. So now here's the crazy thing. At this stage, I think that it's probably okay if you just test numbers, because solving this for n is not always the best thing to do. So test until you find the first n that works, and start small. Like test like n equals 2, because it might be all you need. And it turns out, it's kind of crazy, n equals 3 is it. So if you have n equals 3, R3 is less than 6.4 times 10 to the negative 11th. How did I go 5 minutes over? I'm sorry. Anyhow, add the first 3 terms.